We decided to focus our research around the question, how do the masses of galaxies correlate to other characteristics of those galaxies? For example, do spiral galaxies have more mass than elliptical galaxies? How does the color relate to the mass of galaxies? How does the mass relate to where it is with respect to other galaxies, specifically in terms of environmental density and the distance to the nearest cluster? And finally, which variable has the strongest correlation with the mass of the galaxy?
This chart illustrates the relationship between the mass of a galaxy and the probability of it being an elliptical. The log of the mass is on the x-axis, and the probability that it's an elliptical is on the y-axis. There is a slight correlation between the variables, telling us that the higher the probability the galaxy is an elliptical, the more massive it will be. This scatter plot compares the color of the galaxy to the mass of the galaxy. The x-axis represents the mass in log form, and the y-axis represents the color of the galaxy, with the lower number on the y-axis correlating to a bluer color. After eliminating outliers, there is a slight correlation between color and mass. If the galaxy is redder, then it will probably have more mass. This scatter plot compares the mass of the galaxy in the environmental density. The mass in log form is on the x-axis, and the environmental density in log form is on the y-axis. There is clearly no correlation between the two variables. This scatter plot compares the mass of the galaxy to the distance to the nearest cluster of galaxies. The x-axis is the mass in log form, and the y-axis is the distance to the nearest cluster in log form. There's clearly no correlation. Here's a video simulation of the Andromeda Galaxy colliding with our Milky Way. When the two spiral galaxies collide, they form a new elliptical galaxy. This new elliptical galaxy has the mass of two galaxies, which explains why elliptical galaxies tend to have more mass than spiral galaxies. Also, elliptical galaxies tend to be more red, so this would explain why red galaxies as a whole tend to be more massive than bluer galaxies.
To conclude, before conducting the research and analysis, we made the following hypotheses. We assumed that all variables would have a correlation with mass, and one would be much stronger than the others. We thought that elliptical galaxies would have more mass than spiral galaxies because elliptical galaxies can be the result of galactic collisions. We thought that red galaxies would be more massive because elliptical galaxies tend to be red. We thought that the more dense the environment of the galaxy, the more massive it will be given that galaxies collide over time. And we had the same reasoning for the distance to the nearest cluster. Our findings were that the color and type of galaxy were two variables that correlated to mass, with the strongest correlation for color, and that the galaxy's position compared to other galaxies had essentially no effect on the mass of the galaxy. For this research, we assumed that the mass data we were provided was specifically representative of ordinary matter and not dark matter. Confronting this assumption, a follow-up question might be, how does the mass of dark matter correlate to the characteristics we analyzed, namely type of galaxy, color of galaxy, environmental density, and distance to the nearest cluster? These are interesting questions to us because we cannot see dark matter, so for it to affect characteristics we actually can see is counterintuitive. Further, ordinary matter only accounts for 4% of the total mass of the universe, so the impact of dark matter and dark energy is actually a more significant question statistically.
We learned that science is never at a standstill. It's always evolving. When we created our research question, we thought that a single answer would cover it and that our research would be over. Instead, our research led us into more questions that we wanted answers to, furthering our investigation of the relationships we already found. For example, could there be other variables that affect the mass of galaxies even more? And what if we considered dark energy as a part of a galaxy's mass? Additionally, after answering our initial questions, we also realized how many different ways a single set of data points or even a single chart could be used to answer a simple question. Ultimately, this process helped us realize that there can never be one fixed answer to a scientific question, because the solutions and discoveries never end.